Okay, we're going to be dealing with properties of logarithms, and I'm working under the assumption that you've seen properties of logarithms. Of course, you may pick those up just by writing this, or just by viewing this video. But our first property we're going to talk about is change of base property, which typically our calculators and newer calculators are coming out that handle this for us, but typically our calculators like to work in base E, which is natural log, and base 10. So if we were trying to find, for instance, the exact value of, say, log base 3 of 11, well, I know this is the exponent that turns 3's into 11's, and since 3 to the second is 9 and 3 to the third is 27, this should be some number between 2 and 3, but I don't know the exact value. And what change of base allows us to do is use any base we want. And typically, if we were doing this on calculator, we'd want to use base 10 or base E, natural log. And we can rewrite this as, for instance, I'll use base E, natural log of the argument over natural log of the original base. And it's maybe somewhat surprising. That would be the same as if I used log base 10, 11 on log base 10 of 3, or actually log any base I want. Therefore, rewrite the logarithm as a ratio of common logs. So common log is base 10. We would say this is log 3/4 on log our original base being A. So that is part A. Part B, natural logs, could be ln 3/4 on ln A. And for most of us, unless we have something on our calculator that lets us choose a base other than base E, natural log, or other than base 10, common log, that would be how we would go about finding exact values. Or perhaps if we wanted to graph, say, y equals log base 2 of x, we could enter that as like our y1 value equals log x on log 2. So there is change of base property. Okay, now we're to rewrite the expression in terms of ln4 and ln5, and we have ln 500. So what I would like to do is take 500 and factor it down into 4's and 5's, and then we'll explain a second property of logs. Well, this is conveniently 5 times 100, and I can pick up a 4 here with a 25, or 5 here. So we could write this as ln of 5 times 5 times 5, 125 times 4. Now, one of the properties of logarithms says if we have a logarithm of a product, say a, b, we can write that as ln a plus ln b. And this has a lot to do with, and this isn't a proof or formal or anything, but this has a lot to do with what we're ultimately doing here is adding exponents. And when do we add exponents algebraically? If I had something like x to the second times x to the third, we add exponents. So we see a multiplication which turns into adding the exponents, x to the 2 plus 3. So in this case, we can write this as all of these products can just become sums of different logarithms. ln5 plus ln5 plus ln5 plus ln4, or an apple plus an apple plus an apple is 3 apples plus this ln4. So now everything is in terms of ln4 and ln5. Okay, now in this case, we don't know what B is, and maybe there'd be some kind of inverse process to find out what the value of B is. But if we can write 25 and 9 in terms of 2, 3, and 5, we can get out of this. So I could think of this as log base b of 5 times 5 on 3 times 3. So I can work with some things. I know some things about log base 3 and log base 5. I got some approximate values for those. So the numbers that are in the factors that are in the numerators basically become sums. The factors in the denominators become differences. We talked about sums on the previous problem, but if I had here's a rule. Might as well just give you this rule. There's a rule that says if we have log of a quotient, say a on b, that we can write that as log a minus log b. And we think, what are we really doing here? We're subtracting exponents. When do we subtract exponents? There's a situation where we subtract exponents. And we see, oh, there's division. So not a formal proof, but kind of an explanation why we subtract exponents on this, what appears to be a division problem. So I could start this and just say, well, let's break this into division where this becomes log base b of 5 times 5 minus log base b of 3 times 3, which would be log base b of 5 plus log base b of 5 minus, careful, log base b of 3 plus log base b of 3. And then I can say, well, what do I have here? I really have 2 of these log base b's of 5, but we know that. We know the approximate value. So I could go 2 times 0.8271 minus 2 of these log base b of 3's. 2 times 0.5646. And then we could go ahead and grab calculator if we wanted to, or if, heaven forbid, we actually had to work that multiplication out by hand and then subtract. So if I got some information about log base 2, 3, 5, whatever values, and I can break down my argument into factors of the 2, 3, and 5 in this case, we can get out of this. Okay, now they want us to sketch a graph. And this was kind of, maybe we should have a little bit more background. And there is on a previous video of just a basic logarithm graph. But if I knew what this graph looked like, log 1/3 of x, if I knew what that looked like, I'll call this one g of x. Let's go ahead and think about this function, and then let's just translate it based on this pre-function. So if I was to create a t-chart for this, x, y, and this is just my g of x function I'm talking about here, I would want to choose x values that 1/3 could turn into with an exponent. Because again, this right here is this is the exponent that turns 1/3 into x. Well, 1/3 could easily be turned into 1/3 with an exponent of 1. 1/3 could be turned into 1/9 with an exponent of 2. 1/3 could be turned into 1, as could anything, with an exponent of 0. And 1/3 could be turned into 3 with an exponent of -1. And 1/3 could be turned into 9 by flipping it with a negative exponent of 2. So let's go ahead and plot those, and then we'll just translate the graph. So if I go to 1/3, 1, so here is my origin right here. I'm going to just emphasize that. So 1/3, 1, we have this point. 1/9 jumps up to 2. Right in here, we're getting really close to 0 there. 1 is 0. 3 is -1. And 9 is -2. Let's see, 4, 5, 6, 7, 8, 9 is -2. And what we need to be aware of is what's going to happen is if we're looking at log 1/3, log base 1/3 of x, I can't take a positive value and have an exponent turn it into 0 or negative. So in other words, x is never going to be able to be 0. We're going to get really tight to 0 as we go along, and it may be indistinguishable from 0 for a while. And then we're going to start to zoom out to the right. So that is g of x. So how would f of x compare to that? So we're going to start to realize this is just our base. This is a base function, and just a base logarithmic function. This would look this graph of f would look exactly like g, except it would be 1 to the left. There's a 1-day head start occurring here, or our MyVox that I refer to a lot. Most interesting value of x is when we make the argument 0. Our MyVox is -1. So that implies we're going to shift to the left 1. And maybe most importantly, we shift this asymptote to the left 1. And then this point, this is what I'd call the pivot point, we shift to the left 1. This point to the left 1, to the left 1. Here's one right here. The point that was at 3, -1 gets shifted to the left 1. The one that was at 9, -2 gets shifted to the left 1. So we get those nice defining points. We're hugging along the asymptote. And there we go. Now this is actually to be done on graphing calculator, but I wanted to sketch this guy by hand. Clearly we could do this on graphing calculator, but what we would have to do, because we may not have a 1/3 base option in our calculator, we would have to enter this as, say, our y1 equals maybe ln of x plus 1 on ln of 1/3. Okay, but the good news is our general rules for shifting graphs don't change just because we've introduced logarithms. Use the properties of logarithms to rewrite and simplify the logarithmic expression. Well, we've talked about some of those. We've talked about how a log of a product becomes sum of logs, SUM, sum of logs. So this is log base 2 of 4 squared plus log base 2 of 3 to the 4th. And I could change 4 squared into 16, but I might as well introduce another property that says I can pull this exponent 2 out in front, make that 2 log 2 of 4, and I can pull this 4 out in front, make this 4 log of 2 to the 3rd. You may reference back to previous statements and say, okay, so what we're really doing is taking our exponent 2 here and multiplying it by an exponent. When do we multiply exponents? Well, if I have x to the 2nd to the 5th, that becomes x to the 2 times 5/10. And that's kind of what's going on here. We have an exponent within an exponent. So that is not, again, not a proof, but that's some explanation of why this rule works for us. Now, this is 2 times the exponent that would turn 2 into 4. What exponent turns 2 into 4? 2. So this is 2 times 2 plus 4 times, this is the exponent that turns 2 into 3. I don't know. Log base 2 of 3. I know it's somewhere between 1 and 2 because 2 to the 1st is 1 and 2 to the 2nd is 4. So we end up with 4 plus 4 log base 2 of 3. That is an exact answer. Is that more simplified than this? I think we can make an argument it is. We've made some kind of sense out of this. All right, use the properties of logarithms to verify that this is true. So I have an option here. I could take this 24 and break it into 2's and 3's, or I could take this expression over here and try to smash this together with using our properties in reverse. So I'm going to say, all right, let's see if ln 24 can equal, this would be negative, and I could make this ln 2 if I brought the 3 in as an exponent. That's one of our properties. Plus, oops, sorry, ln 3. That's bad. And then our rule for sums of separate logarithms become products of those. This is negative ln 24 equals, I sure like this negative. This becomes ln 2 to the third times 3. And that, of course, is negative ln 8 times 3, 24. So we get it that way. Like I said, though, we could have taken this side and turned the 24s into 2's times 3's. And, of course, 24 factors very nicely into 2's and 3's because it is 4 times 6 or 2 times 2 times 2 times 3. So this becomes negative ln of 2 to the third times 3, which becomes negative ln of a sum, 2 to the third plus ln 3. Pull the 3 out, and we get our negative 3 ln 2 plus ln 3. They're really pretty easy to work with just a very little bit of practice. Okay, use the properties of logs to expand the expression into multiple logarithms with simplified arguments. Right now, I have an argument of x, y on z. I want to simplify that. Okay, if the entire numerator is factored, entire denominator is factored, all the factors in the numerators could be summed together with different logarithms. So this is ln x plus ln y. And anything that's a denominator could be subtracted from that with the ln in this case, minus ln z. And in that case, basically, other than the extraneous parentheses, this would be what we're looking for. And I don't think it's a stretch to think we can jump from here to there. And now, is our arguments as simplified as they can be? Absolutely. Okay, bonus problem along that line. What if I had to simplify, say, this argument? What if I had x squared minus 4, for instance? What you cannot do, so this is just an example, has little to do with this, same directions. What you cannot do is distribute ln. This is not ln times x squared minus 4. This does not become ln x squared minus ln 4. These rules work with factors, but I could write this as ln x plus 2 x minus 2, and that, because there's factors in here, would be ln x plus 2 plus ln x minus 2. So the key is we need factors to apply this property. So I see everything's factored. I got a factor of x. I got a factor of y to the fourth. I've got a denominators factored into just z to the fourth. One thing you're going to find out quickly is don't really like radicals mixed with logarithms. Radicals and exponents work out well together. So we might want to think of this as log base b of x to the 1/2 y to the fourth on z to the fourth. In which case I can look at the numerator. It's a product, so that becomes sums. Log base b of x to the 1/2 plus log base b of y to the fourth. And then my denominator we would subtract. Log base b of z to the fourth. Exponents can get pulled out in front, giving me 1/2 log base b of x plus 4 log base b of y's minus 4 log base b of z's. And there's no way I'm going to get simpler arguments than just plain old x, y, and z. Now this is the opposite of what we're doing. Now we want to smash everything together. And to smash everything together with a subtraction, our property in reverse of what we were just doing would say we turn that into a single logarithm of a quotient. But before I do that, I'm going to clean up this minus 2 by bringing it in here, bringing the 2 in there. And now that gives me single ln of x on x plus 2 squared. Okay, now what if we were thinking of this problem as, so here's an option, what if we were thinking of this as plus negative? Let's see what happens there. That would be ln of x plus ln of x plus 2 to the negative second. The rule for sums, say we smash these together as a product in a single ln, and I get ln of x times x plus 2 to the negative second. But that, of course, is ln of x on x plus 2 to the positive second. All right, here is a monumental common mistake. Happens all the time. We get from, it's right here, we go from here, instead of writing this as a single ln, I will see people try to turn this into ln x on ln x plus 2. Hopefully you're listening to this, or 2 squared. Hopefully you're listening to this and not just watching it and thinking that's correct. If you are, make certain that is no good. This is this ln of an ln minus an ln, or a log minus a log provided at the same base, becomes a single log of a quotient. Okay, so once again, we're trying to smash these things together. And I'm going to claim if you get clever with this, we could do this in one step. But I'll go through the multiple steps after we do this. But I know 3 can come in as an exponent, 2 can come in as an exponent, 4 can come in as an exponent. I know this makes these products of the numerator, or factors of the numerator, that's factors of the denominator. So this just becomes single ln, I need a fraction. My numerators, x cubed, y to the second, my denominator, z to the fourth. But if we want to go through step by step, this could be ln x cubed plus ln y squared minus ln z to the fourth. And that could be ln of the sum becomes a product within the function, within the ln function, x cubed y squared. And then the difference becomes a quotient. Single ln, not ln on ln, just ln of something on something. Again, I just showed it on the last frame, but I'm going to show it again. Common mistake would be to jump from here to say, oh, that's a quotient, so it's ln of x cubed y squared on ln of z to the fourth. People do it all the time. Not in my class. We're not doing it. Okay, how about this big mess? Well, I suppose I'd start, if we're trying to turn this into a single logarithm with a lead coefficient of 1, I might as well get this 1/2 taken care of. So this becomes 1/2 ln x plus 1, but that could be ln x plus 1 to the 1/2 plus distribute 1/2 to 2. Well, that's pretty convenient. ln x minus 1 plus, bring the 3 in, ln x, whoops, that's bad. Try that again. ln x cubed. And then I see everything is a sum, so each of these within our individual ln will become a factor. So that is ln of x plus 1 to the 1/2 times x minus 1 times x cubed. Only thing that may change in this is perhaps we would maybe do a little rearranging. X cubed, x minus 1, but what I wanted to show is maybe you would see this as an answer, square root x plus 1. Either of those guys. Okay, so now we're base E, we're natural log ln's. Find the exact value without a calculator. Holy smokes, I don't even know what the exact value of E is. 2.71, something like this. But what can we do here? Let's smash these guys together. ln e to the 6th minus ln 2 can come in, so that would be e to the 5th to the 2nd. That's e to the 10th. And then we got to say, well, what's going on here? This is, I mean, I could smash these together. ln, that would be e to the 6th on e to the 10th, which is ln 1 on e to the 4th, or e to the negative 4th. And then it's like, how do I know the exact value of that? Well, what is this thing? This is the exponent that turns e into e to the negative 4th. Well, what could that be? I need an exponent that will turn e into e to the negative 4th. Wonder what that could be. This, of course, is negative 4. But did we have to do all of that? What is the exponent that turns e into e to the 6th? 6 minus 2 times what is the exponent that turns e into e to the 5th? 5. 6 minus 10, negative 4. I love factors of e with ln's, with natural logs. Okay, hope that was helpful for you. Probably something you didn't need to see right there, but that's the mess I create, letting you inside the world of the purple-shirted nerd. We're not going to keep these. Stay tuned. We'll have more on logarithms soon to follow.